So the topics we'll be going over today will be a review of deep learning, going over distributed training, reinforcement learning, the machine learning ecosystem, a new framework from UC Berkeley that I was part of a course curriculum with called Ray for distributed Python, and Intel AI. We'll take 1 hour of questions afterwards. First off, though, I'd like to understand more about the audience, so I'm speaking at the right level. How many people here have experience with machine learning? Is everyone here? Reinforcement learning? So I can probably skip the overview of the basics of reinforcement learning. And distributed training. Okay, so that one will be new. All right. Okay, so the reasoning behind distributed training is that deep learning, as you know, is very computationally expensive. It can sometimes take a few hours up to a few days to properly train larger networks, and so there's a big push with companies to reduce this time. The issues is that it requires a lot of memory to store all the activations, the weights, and the data set itself. Along with, you need fast processors and the memory bandwidth. But the process of distributing this across a data center is quite difficult because the training process is synchronous. You have to wait for the forward pass to get all of the activations which are required for the gradients for the backward pass. One way by doing this is, if you're familiar with mini batch learning, is to spread the training across copies of the model on different nodes, and then you average the gradients to a central parameter server, and that acts as mini batching. This is kind of an issue because with many workers, the average gradients will become noise, so they don't help you. And then as you have a longer training period, the models diverge from each other because they will find different local minimums or different representations of the information. And so as these models diverge more and more, the average gradients will also become noise. So you have to find this careful balance between the model training time and the cost of having to average all of the weights, or the update method, and then the communication time. The example here is the Horovod system made by Uber. And you have, on the first case, one parameter server. And then you have another case where you have several different parameter servers. You might average different portions of it, and then maybe pick the best selecting model. Another one is Ring All Reduce, also by Horovod, where instead of having a parameter server, it utilizes the fact that each worker has the same model architecture, and that means that you can exchange the gradients between the workers themselves, reducing the need for a central parameter server. So they might exchange parts and continue training. That way there's a central model between them, but there's no parameter server. That reduces the time required and reduces the I/O cost. And one of the last major ones is model parallelism, where if you have a complicated model, you can split the model itself across different nodes. And in that way, on the example on the left, you have model parallelism, and an example on the right, you have data parallelism, like the weight averaging we talked about. But say you have a complicated model, such as a super network or a GANs, you will train different parts of that model on different nodes, and then use that information through a technique such as a parameter server to update the different parts. This can be very helpful for situations where the model is too large for the resource capacity of the node you're on. Seems everyone here is already familiar with reinforcement learning. A little recap?
I suppose most people know it, but it's fun to see it twice.
Okay. Is everyone here familiar enough with reinforcement learning that I might explain about how to distribute DQNs? Everyone heard of a DQN before?
No. Yeah,
no?
Some people haven't. So yeah, that would be a good one to
okay.
get into.
So a DQN will start off by getting a lot of a history of what different random actions do in a game. And what it does is actually I should probably start off with a little simpler approach. With reinforcement learning, you get the you get a different type of learning as compared to a classifier, by which an agent will perform an action in an environment, get back the state and reward. And so this imitates the way that animals and people are able to learn from their environment by getting a reward back by performing different types of actions. So for humans, this might be things like a physical reward, or food or drink, a neurological dopamine, or social rewards. And so you can theorize that our actions are based upon maximizing these rewards. We use games because it's quite difficult to come up with an accurate function to represent a biological reward. So instead what we use is the return values from games, because not only games require things such as strategic planning and an understanding of their environment, but then it's a very easy way to get it back in terms of points, whether or not you lost the game. We don't have to build anything that might mimic how complicated it is for something that's biological. So in a DQN, what happens is that it starts off by choosing random actions, kind of like testing out to see what different things do, like we do when we start playing any new types of games. And then it stores those actions and what was going on in the game in a history. And then it learns from that to understand which things will affect the policy or the behavior of the agent in the game. And the point of a DQN is to make an agent that has the best policy, one that can master the game based upon learning from the history. Or so most people understands what a DQN is and the basics of what the algorithm is trying to do. And so can anyone point out in what step is it that we can distribute this? What part of it is not serial that we can distribute across multiple processes to make it go faster and learn in a shorter amount of time? You might notice that within this for loop, we are selecting an action in the emulator and then getting the reward back along with what's going on in the environment. This process can actually be spread across multiple nodes or workers. And so we're not actually updating the target network until this step down here, we're performing gradient descent on the action value function. And so one of the ways we can speed this up is by distributing this process that's in this for loop to multiple processes or multiple workers. So it does this asynchronously and then resets the target action value function. This will dramatically speed up DQN training. So just looking at how reinforcement learning is different from regular supervised learning can tell us about why it's easier to do this on a data center scale or on a very large CPU system as compared to just a workstation with a few GPUs. The main point about why it's different is that the training and inference happen simultaneously with normal deep learning training. It's the training first and then inference. But when you have the training and inference simultaneously, the inference has to be run in a simulation. Now, the simulation is usually more complicated operations that are not just the simple matrix operations that are done on a GPU. In fact, it requires more complicated processing that slows it down when you put it on some types of accelerators. A CPU can actually be 13 times faster than a GPU, which is very unusual in comparison to how it normally works in deep learning. This is because the simulation has to be run while it is training, so training time takes longer because it requires more computation. To put this a little simpler, when it's training, it has to run this in the environment, get the reward signal back, and that process of having to run it in the environment, that is something that when it's distributed across a data center is very easy to do. But when you put it on something that normally works on regular matrix operations that you would find in deep learning training, this becomes very hard to do and it takes longer. To look at different ways that distributed systems are used in machine learning. One of them is model serving. So say you have an application that has a few million users. How can you effectively use one model without having to, how do you get all the user requests to access that same model? Well, you can't just copy that model over to everyone's phones. So some of the applications include model serving, which they can submit requests to your system. Another way distributed systems benefit AI is through data processing. So the normal ways in which we usually think about big data and data clusters, which would mean that you have access to more resources, access to more data storage, and you can have multiple compute nodes. Most of us should be pretty familiar with these types of applications already. Another one is hyperparameter search, because one of the main issues is that these tests, when you are testing out a new machine learning model, it takes a very long time to test because say you're trying to figure out which configuration works best for training, but your training test takes a day to run. Most CNNs could have anywhere from 20 to 100 different hyperparameters that you have to tune to get the correct performance. And so this is where you can run your tests on many different nodes at the same time instead of just running one on only one node. Another thing might be the system itself, so not just how your model is set up and the model topology, but things like your framework version. The newest framework is not always the fastest. Sometimes older frameworks, the operations might be faster if you go back to last month's version of TensorFlow instead. So when you're trying to fine-tune your performance, you have to look at the framework versions, the system configurations, the number of OMP num threads, the number of CPU threads, and interop threads are not just set due to your system configuration. Those actually have a very high influence on the performance of how well your system will do in terms of training time and inference. Federated learning is something that's gaining a lot of interest because of privacy concerns. Say you have an ML model that is trying to learn about information that is stored on people's cell phones or on different hospital data centers, but that information cannot leave your cell phone or the hospital. So federated learning is centered on how do we train a model on data that we can't actually access the data at a central point. So it's like sending out copies of the models to the different data sources and then sending the gradients back. But that could become an issue if, say, you have an unbalanced number of different types of classes on any one node, because then your gradients will become, they will not be trained on the correct data. So this is gaining a lot of interest in the distributed systems field. And this is where Ray comes in. It's this new framework. You might notice that all of the different things I've mentioned about distributed systems, they have many tools. And for machine learning engineers, they have to go out and learn all of these tools. But who's going to expect you to have to learn Spark and to learn all of these different tools in order to do distributed systems into your job when you already have to know all the things required for a machine learning engineer? You would need a team of system engineers and as well as machine learning engineers. And so Ray was created to essentially simplify the entire process by being able to use the same framework for all of these different tasks. So you can use it for hyperparameter search and data processing and reinforcement learning, model serving and distributed training, unlike all these other things which are used to only serve that one type of application. So it's a general purpose framework that can do all of these different functions. The API is written in Python and it's quite simple. These few lines of code are actually distributed Python. If you're familiar with having to use distributed Python before, it becomes quite messy if you're trying to exchange information between different nodes or sending information to different servers. You can imagine this might take many months to try to set up. This was set up in such a way that all you have to do is put a decorator at the top of the function, and it automatically makes that function a remote function. You don't have to change any of your code. Whenever you call that function, it returns an object ID to whatever that function returns, and you can call it with ray.get. So in this case, the function zeros might be done on a different node in the cluster, and this might be done at a different node. It returns the IDs to the dot function, which can be done locally or on an entirely different node, but then you still get it locally. So this whole thing can be run on 3 different machines, but it's only about 10 lines of code. If you've had to use distributed systems before, this vastly simplifies the process.
Just a quick question.
Yes?
Does it take care of global variables?
Yes, it actually does. I remember trying to write some distributed frameworks before and trying to understand what your function needs in terms of global variables and libraries is very difficult. It automatically figures out what it needs. So for instance, you notice that in the function it doesn't say import numpy as np.
Yeah.
It automatically will realize that numpy is required and import it in your worker node.
So does it copy from their remote, from a local system to the remote server, or?
No, it assumes that the remote system already has
But
this
there
one.
could be some other global variable also, like, I can define something and it has to copy that thing maybe.
Yes, it does copy that. I'm going to go to the architecture of how this works in a few slides, but it does share those variables between nodes. You can also store states instead of just functions. So this makes it very easy if you're trying to do things like parameter servers. In this case, you can mention the amount of hardware you want to allocate to that particular function. So in this case, we want it to use only one CPU. And this can be run remotely as well. All of these, the only things we change are just the .remote. And then when we want to get it, these are just the IDs, but when you do ray.get, it returns to the actual value. So if you can imagine removing anything that has the word, remove everything that is purple, this would work just the same as it would locally. The only things you are changing are the decorators, and whenever you call it, it says ray.remote. And you might also notice that you don't have to, when you put in the IDs, in the last one, you notice it says ID1, ID2, and then it goes into the argument for dot. Over there in the np.dot, it does not say ray.get A, ray.get B. It smartly realizes that it's getting an object ID, so it does not have to do any complicated systems to try to deal with object IDs inside of these remote functions. It's essentially just the same as it would be for a local system. Yes?
Yeah, so we don't have to just get a variable and feed it to another function. We can just get the ID and use it for next function. And
yeah. Say you had say that your remote function calculated a really large piece of data. You don't have to transport that back to your local device. It's just giving you back the ID. You could essentially be plugging in a Raspberry Pi as your local device into a cluster, calling something that's a few terabytes, and then it already sends that over. It's not on the local machine. It's counting states, which is very important because say you have to communicate between the different workers, or you have to send flags to a centralized place and execute different commands across. This makes it very simple to create like remote functions within remote functions and very complicated dependency trees. If you might notice, the only ray functions that we're dealing with are the things in purple, which is only about 4 different commands, but they are general purpose enough that you can create extremely complicated systems. I've implemented almost all of the distributed training methods I mentioned before, so weight averaging, and then the ring all reduce. I've implemented all of these just using those 4 commands and run them on entire data centers without having to modify anything else in my code. If I remove these purple sections, it would run on my laptop with just the same. This is how the architecture works. So these green sections are different processes. And then this answers the question before about the object store, where it can store the object IDs. This is where the actual data is. The IDs you get refer back to what's being stored in this section. The object manager can communicate between different nodes. So say this worker wants a piece of data with a certain ID, but it's actually stored on this node. Well, it can go through the object manager, which checks this object store and returns it back. And then the scheduler can also look at things like the resource is going low on this one node, we're running out of CPU, we're running out of memory. It's able to warn you if that's happening, and will also be able to allocate new workers to some place that is not, has more resources available. It essentially does all of the things that you would think of having to implement by using Kubernetes and Redis and how to share data between nodes and an orchestrator. It does it all in the background, and the only interface you actually have to see are just those 4 commands. This usually requires an entire team of system engineers to set up. And this is something that's probably the best for people who are trying to develop new applications and new training methods, so you don't always have access to a cluster. The difference between running this on your laptop and running this on a data center is just one line. In this case, the Redis address refers to like when you start up Ray, it tells you what's the address of the head node. You put in the address here, and it realizes it's on a cluster. It'll share this across the entire data center. But in this case, on the left, this is running remotely. You can emulate multiple workers and multiple machines by multiple processes on your laptop. It will still operate in the same way. So the advantages are that if you're having to deal with multi-threading in Python before, you're probably familiar with this type of nomenclature where it starts up another process, but the T variable in this is just the actual thread. It's not the object ID. You can't get the data back that's being calculated on this thread without having to use a complicated system of global variables or a parameter server. So Ray already solves this issue. And also, you used to have all these issues where the global interpreter lock is what manages multiple Python processes. And you run into a lot of issues when you have frameworks that are meant to take advantage of this. So for instance, if you run a NumPy operation in a thread, it'll mess up the GIL and it will sometimes get 10 times slower when you try to distribute it. You don't run into this process when using Ray, which is very advantageous. This answers the question before because about dependencies within functions. It will automatically figure out what that function needs and it will serialize that or will import it on the remote node. Aside from that, there's a few things which have to be taken into account. You don't want to put a large data set into the argument because when things are shipped over to another node, they have to be serialized and then stored somewhere globally. When it's a large data set, that might take up a lot of space. So you want to import that data set later on in your function instead of having to pass that in as a regular argument. Another thing is that TensorFlow sessions cannot be serialized, so you have to have multiple sessions working simultaneously. I had a project that was using Ray where it had over 150 TensorFlow sessions, all working simultaneously. So it can be done with multiple processes. This is a parameter server in 10 lines of code, which if you have to build parameter servers before using sockets, it's usually hundreds of lines. If you've tried to use distributed TensorFlow before, this also uses hundreds of lines. In this case, it's human readable, and the only thing I did that would change it from a regular Python class is just add the decorator at the top. The rest of it is already set up to be run distributively. I've used Ray before in the past 6 months for a project that came out of MIT and Harvard where it was genomics mapping. I was able to increase the speed 2.5 just by distributing it. I've tried to use Ray to use that as the backend instead of Intel RL Coach, which uses many different frameworks. I was trying to simplify it all by just using one framework. And this is quite interesting for anyone here who has to deal with research in inference. So if you're in robotics, or if you're in anything where you're trying to use the output of a model, you can increase the speed by 8 or more just by using a distributed inference engine. So this is like when there are multiple copies of your model and then they are all running inference and you're feeding in it snippets of it and they're all running at the same time. This greatly speeds it up. Instead of just waiting for one model to get one frame and then waiting to get the other one, it's processing, you can process hundreds of frames at the same time and get the outputs of it instead of having to wait one by one. An overview of the frameworks available. You can classify these into two different groups, ones that are based entirely upon the algorithms and another one that's based upon the environments. These are the different, the similarities that you find between these different frameworks. Usually algorithms can be more terminal based, or you get like a really nice Python object API where it just says, like, here's my agent, agent.run, something extremely simple. Algorithm-based frameworks usually do not include the environments, and they do not try to build new types of environments. They allow for customizations, and then for environment-based ones, usually just based on one particular game or one subset of games. You can also plug it into more complicated systems like game engines, where you can provide the feedback back to your model. I just spoke about RL Coach. This is one which is more of a industry tool for testing out a really large variety of RL agents on a lot of different environments. So 32 different algorithms already come pre-made on Intel RL Coach, and it supports OpenAI Gym, Vizdoom, RoboSchool, Carla, StarCraft II, the DeepMind control suites, and extensions to Gym as well. This one is terminal-based, though. It's not like most of your RL frameworks where you can interact with it in Python. This one's really meant to be run just by terminal commands, where you have your configuration settings as arguments. You can switch between your deep learning and backend. So say you don't want to use TensorFlow, you want to use a different framework instead, like Caffe or PyTorch, you can choose to do that one instead. Maybe it works really well in your system and you want to do something you're familiar with. And this is an example of the visualization of the training results. Going back to Ray, this was an application or a framework that was built on top of Ray called RLlib. And this is very simple to use. It was what I was talking about earlier, where instead of having to write your own training function, you just do agent.train, and then it runs in the background using that same sort of environment simulation rollout that we talked about before with the DQN to speed up training, where it's collecting it's collecting the results of the simulation asynchronously. And then it's also advantageous because it uses another application called Tune. So instead of having to manually figure out how are you going to do all of your hyperparameter tune-in, like what's your learning rate, what's all of the different arguments you're going to feed into it, the things that you might have to test after you know that your agent works, just to make sure that it works the best it can. You can use Tune to run these experiments for you. In this case, it's looking for the learning rate using a grid search between these three different options.
Just a quick question. That sounds really cool to me. If you can just specify site like this.
Mhm.
So does it store results for everything? For each configuration, it stores the separate results?
No. Yeah, it will give you back the results of, like in this case, it's policy optimization, running cartpool, and the only thing you're trying to change is what do these different learn rates result in. It also has a lot of different ways, not just grid search, but smarter ways to try to find the best results. So instead of having to manually change it over and over again on your cluster, this one you set up how many nodes you want using the RAID terminal interface, and it will automatically spread this across. It saves an enormous amount of time. And you can run it on your laptop as well. This one is quite popular. It's Google Dopamine. This is their RL framework. Now, this one does not focus that much on implementations of agents. The examples you have are most likely going to be community-based. It only provides you with implementations of DQN and Rainbow agents, which is unusual for such large of a framework, because usually you have a large collection of an A3C agent and maybe a dual and DQN, but in this case there's only two. And it uses a Google framework for configuration. So what you feed in for your configuration is actually this string here. This you don't find very often in other frameworks. This is from DeepMind. It's nicknamed Truffle. This is not actually an RL framework in the traditional sense where it provides you a bunch of agents and pre-made algorithms. What this is an extension of TensorFlow to include all the different types of operations that you find in RL. So if you want to build something from scratch and create new types of RL agents, you might use this to include to the TensorFlow library. TensorForce looks very familiar to RLlib in that it's the same sort of thing where the agent is within a class object and then your configuration settings might go in as arguments to that object. A very Pythonic way of implementation. This one is interesting because you can actually run it in Unreal Engine 4. This is one of the few frameworks that allow for this. When it comes to environments, so the things that actually let you have the simulations, not the ones that have the RL agents themselves. The most popular is by far Gym. It's made by OpenAI. You're most likely familiar with this if you've had to make any sort of applications in RL. Very large number of environments available, from anything from the really simplified versions just to check to make sure the RL algorithms are working, to simple games, all the way to Atari games, and more complicated ones such as robotics and Mujoko, which is a very sophisticated physics engine. You will most likely be familiar with the humanoid. You see this one in the news a lot. It's one of the most popular simulations of robotic dynamics. These are the environments that are given by Google DeepMind. So you have Lab, which is for maze and puzzle solving. You have StarCraft II. This was in collaboration with Blizzard. You might have heard about this one recently in the latest AlphaStar. And then the DeepMind Control Suite, which also uses Mujoko for different dynamics problems. So trying to have someone learn how to stand up and walk around without falling down, how to run around things. The Unity ML Agents Toolkit is somewhat unique in that you can actually use Unity as not only as a game engine, but you can create new RL environments for it as a Python plugin to the actual engine. So you can create the environments that you want your RL agent to work in. VizDoom is a pretty simple one where it's able to play the game of Doom and then give you back the value for RL agents. This one introduces something that you'll find a lot, which is that it gives you extra sensory data. So your classifier telling you what the different objects are, maybe a depth map, and then maybe a map of where the agent is in a global sense. This one is Carla, which is a very realistic automated drive-in simulator. The same sort of thing as VizDoom, where you get a depth map and a object segmentation of what the different objects are, and then you have a 2D view of the radar around it. And the idea behind this one is that it's realistic enough that when you create an RL agent, you can put this in the real world, and the simulation is, close enough that you might be able to train it using the simulator and then use that same network and put it in an actual car. By the numbers, you can tell you which sort of frameworks are most popular to use. I have them arranged by their popularity. Gym is by far the best, by far the most popular environment to use. In this case, it's interesting because Dopamine has the one with the most GitHub stars, but the number of commits to the repo have gone down, which suggests that Dopamine may be most popular just because it's from Google and it's a well-known name. So which one do you use? Each one is for different skill sets. OpenAI's Gym is for people who are just starting in RL. It's a very simple interface. But then the other ones all have their own different advantages. So say you wanted to have very complex physics simulations, you might use MuJoCo, or for different tasks you might want to use a more sophisticated game engine to get different type of variables that you want. Which one do you need to know is most likely Gym, because it's used in almost every RL framework, includes an interface to Gym. But there isn't quite an algorithm framework that has come out on top. The community hasn't decided on which one to follow as they have with Gym. Now the question of why is Intel so invested in AI? I realize that other companies maybe have a bigger spotlight on AI, such as Google or NVIDIA. But some things you may not know about the company is, for instance, Intel sold more than $1 billion in AI hardware as compared to about 606 million reported by NVIDIA. You always, a lot of the time you will think of AI hardware as dealing primarily with GPUs, but then when it turns out in the actual market, the companies are going to be using the data centers. Because when you're stuck on a workstation, you might be using a lot of GPUs, but when you have the full scale of a data center, they'll be using a lot more of that type of hardware. Intel has invested very heavily in AI. It's acquired many different companies, including Mobileye, which does automated drive-in, invests in robotics and computer vision. 3 of the top 5 ImageNet inference records are actually from Intel. So it may not be known as much for training, but also for inference, it's known to be incredibly fast. The Stanford DonMetch is a third-party group from Stanford that has global competitions between researchers to see how fast they can hit a particular benchmark. And reinforcement learning has been found by the MLPerf Research Association as being 13 times the speed of a P100 GPU, which is which can be surprising to a lot of people until you think about how the simulation rollouts really affect the performance of RL on a GPU, because GPUs were made for these very large matrix computations, but environment simulations, it's, for instance, an automated car drive-in is a lot more complicated than just doing a forward pass. And in terms of the number of types of hardware that Intel invests in, we run AI on FPGAs, vision processing units. This next one, the neural network processors, is a collaboration with Facebook to create a special type of accelerator. Quantum computers and neuromorphic computers, which are, instead of taking the idea of how the brain works and incorporating the software, it actually incorporates the idea of how brains works into hardware. So for instance, imitating how the brain computes through spiking and other, like our mathematical approximation of how we assume neurons work, not just deep learning. We actually make over 120 different types of AI hardware. This is the Intel GPU from 2020. This is that brain-inspired hardware I was talking about, some quantum computers, the Xeon CPUs, and probably familiar with the Movidius inference NICs, which are these USBs that you can run inference on your models without having to use your laptop resources. So the idea is you have all these different types of hardware for each stage of an AI application. This is why you find it in the market, like in the actual industry, as compared to just a research training, because you will have to use these types of hardware from each step in an actual AI application. These are the different type of companies that partner with us on AI ventures. Probably recognize a few of those. And then this is where I talk about how I can help you. I work with different universities and students across the world to help them get educational material, but more than that, we also offer cloud compute resources, such as the AI Dev Cloud, which is you have access to a compute cluster with Xeon scalable CPUs. Each node has 96 gigs of RAM, and each user can use 200 gigabytes of storage. And each user can use 5 nodes at a time for your compute workload. Student Ambassador Program is where you get connected with different students around the world to help with research collaboration, or you also get help from Intel, and then you also get to know about the frameworks that Intel creates and the new optimized software and the different projects as soon as they come out. And then we also participate in research grants, and you can also get hired while you are a student with internships and AI fellowships with the multiple AI different departments, such as Intel Labs, AIPG, or with different departments that specialize in experimental hardware on which AI software is run, like quantum computers and neuromorphic. So some recommended further reading. So there are a lot of free educational courses available with the program that I work with. So this would be on the Intel Developer Zone. We have courses in machine learning, deep learning, computer vision, anywhere from introductory level to the graduate level. But other courses that I might recommend online, UCL's reinforcement learning course, the Stanford's convolutional networks course, and the deep learning book by Ian Goodfellow. are all fantastic resources I would personally recommend. And then we also have a course that I just worked on that was specifically about Ray. It provides about 8 different modules on the beginning of distributed Python programs to very complicated, how do we get a distributed task within a distributed task and so forth, and how do we create reinforcement learning applications. If you want to find a copy of the full lecture slides, since I went over most of it and just summarized it instead of explaining all of the points, you can search for the public repo on GitHub. And now it's time for any questions.
Are there any questions?
I'll just ask a quick one. Since you have experience implementing Ray,
And what was that?
since you implemented some algorithms using Ray,
Mhm.
I'm just wondering how is your experience in debugging your algorithm when things start getting wrong? So by the time things are working fine, it's okay, but when things don't work, how is it?
Like how do you debug distributed systems?
Yes.
The error message actually show up on your local.
So that's fine, but
yeah.
is it still convenient, easy for you to?
It's just as easy as making any other Python research project.
Okay.
Sorry.
Related to that, does that include input and output? Can you do things like breakpoints and interact?
That's right. Yeah.
Oh, does Ray allow for breakpoints? You can. It tells you when a worker function has stopped, and so it won't just like continue running in the background and not tell you if there's anything wrong with that worker. The error messages from that remote function will also show up locally. So even if that process is running on a different node, if something goes wrong, you'll see the error message on the head node.
Just to add to that, can we add breakpoint to that, to our code and run it on the server?
I've not worked with that, no.
So like Kubernetes has like a nice like dashboard, and like you can sort of like do a lot of things with this like graphical UI that they show you. Does Ray have something like that too, because it uses Kubernetes under the hood?
No, it does not.
Okay.
So for the Ray, they will ultimately fix out the mutex log, something like that, the parallel problem.
What was that?
Like the mutex log, something like that. The parallel computation problem.
No, you're not going to have to be working with that.
Okay, so all of the thing will be automated. So
It runs completely in the background. You don't have to deal with things like that.
I'm wondering about Ray implementation. The driver node obviously has to have all the code, but how much code is downloaded to each of the workers? And is it downloaded at the beginning or as needed?
No, it's as soon as you call the remote function, it serializes just that function, and then it sends over that one snippet that it has to do on the remote.
So it basically sends the code as needed.
Yeah, not the entire file or the entire file system. Which also means that if you require other files, it's not going to be sending over.
I believe Ray came out of Michael Jordan's lab, I believe.
Ray came out of a Rise Lab. Yeah.
Yeah, Michael Jordan had a lot to do with this. They made Spark as well. Right?
Yes, it came from the people who originally came out of AMP Labs, which created Apache Spark.
So it's a really well thought out framework.
Mm-hmm.
Probably assume it's going to take off.
The project is managed by Professor Ian Stoica, who was one of the founders of Databricks, if you're familiar with that large company.
Just one more. So if I don't use Ray right now, I don't have any alternative, right, other than writing the whole code myself. So do I have, is there any alternative?
There are some alternative Python distributed frameworks, but this is the easiest one I've come across. You can use things like Dask.
Yes?
Dask. That's another distributed Python framework. And there's other ways you can do it for particular types of workloads. Such as if you were doing distributed training, you could use distributive TensorFlow.
So what would be your recommendation if somebody here wanted to get onto DevCloud and play with Ray? Would you recommend that course, that 8-segment course?
For learning how to use Ray, yes, I actually wrote an article which is on the Rise Lab site on how to use Ray on the DevCloud. It provides an example of using RLlib to learn Atari games.
Yeah, I go through one or two example use Ray and RLlib. It seems that you should update the GitHub because there is some very like package problem you should solve, something like that. And the Ray is kind of a newest version and it cannot fit many package. So something like that, yeah. But it's pretty cool. You use several CPU to do that things.
Were there any other questions?
All right, well, let's thank them one more time.